Hi everyone, my name is Yutana Tumnoy from the Office of Atoms for Peace, Ministry of Higher Education, Science, Research and Innovation, Thailand. Today I'm going to talk about the long-term investigation of radiological impacts on the economic marine species in Thailand caused by Cs-137 released from the Fukushima Daiichi nuclear power plant accident. Here is the content of my talk. I'm going to start with the short introduction about the Fukushima accident in 2011, followed by the sample collection, sample preparation, and the sample measurements. I'm going to show you a bit about the basic concept for the radiation dose and risk assessment in biota, followed by the results and some short discussion over the obtained results. And I'm going to end up my talk with the conclusion. As you all know that there was the massive earthquake happening in Japan on March 11 and 2011, followed by a massive tsunami with the wave of 40-meter heights hitting the Fukushima Daiichi nuclear power station. It caused the cooling system to fail. It means that there is no system to pump the water to cool down the reactor core to preventing the reactor core from melting down. Therefore, the Japanese decided to directly inject the water into the reactor core just to cool things down, to cool the reactor core down, to prevent them from the melting down. Otherwise, the consequences might be a lot serious and cause the huge damage to the reactor building. But by doing so, it caused the hydrogen explosions blowing up the reactor building, leading to the release of a huge amount of radionuclides, including iodine-131, cesium-134, cesium-137, strontium-90, and so on into the atmosphere. Once it enters into the atmosphere, it's widely dispersed across the Pacific Ocean and across over the several countries, causing the radioactive contamination in a wider area, not just only in Japan. But at a certain point of time, the radionuclides deposited on the sea and ocean due to the dry and the wet deposition, causing the radioactive contamination in sea and ocean, leading to a possible increase of radiation doses received by the marine organism living in that particular area. In addition to the atmospheric release, there also was the discharge of the contaminated water into the Japan Sea and the Pacific Ocean. It led to the radioactive contamination on top of the fallouts from the atmosphere. This caused the radioactivity in the seawater in the marine ecosystem to increase a lot higher than the background level. Shortly after the release of the artificial radionuclides into the environment, like iodine-131 was the radionuclide of concern because of the a large amount of iodine-131 was released into the environment, but few weeks or months later, iodine-131 decayed away from the environment because of its short physical half-life of 8 days. But after that, Cesium-137 became a radionuclide of concern because it lived a lot longer than iodine-131. It has a physical half-life of 30 years, and it can dissolve in the seawater. Eventually, it can accumulate or it can be taken up by the marine species into their bodies, leading to the higher radiation doses in their body as the result of this radioactive contamination. Once they receive higher doses in their body, some kind of radiological impacts could be observed in those species with the increased radiation dose in their body. By having said that, the objective of our study is to investigate the long-term radiological impacts on the economic marine species in Thailand caused by the Cesium-137 from the Fukushima nuclear accident. Here is the sample collection, sample preparation, and the sample measurements. We basically conducted this study during the period of 2012 to 2019, which is 8 years in total. We collected the 20 liter of surface seawater and 3 different economic marine species, including Nemitoras hexodon, Saurida elongata, and Loligo dubosile from the Gulf of Thailand, and also from the Andaman Sea. We collected the 20 liter of surface seawater using the water sampler, and once we got the sample, we took them back to the lab to get them filtered and to use the ammonium molybdophosphate or AMP technique to precipitate or to extract the cesium-137 from the seawater, followed by the gamma counting using the hyperpure germanium gamma spectrometry with the counting time of 80,000 seconds. Here is the sample preparation for the Cesium-137 analysis in marine biota. We collected 1 kilogram of each marine species and took them back to the laboratory for the preparation using the fish dryer, followed by the sample packing using the plastic container, followed by once again with the gamma counting using the hyperpure germanium gamma spectrometry with a counting time of 80,000 seconds. Once we got the radioactivity information or data, we did the dose calculation using the predictive model that freely available for everyone to download. But before we introduce that software to you all, we are going to, first of all, we need to understand the basic concept of the radiation dose assessment and risk assessment in marine biota. On your left-hand side, you can see the flow chart of the radiation dose and risk assessment. In order to do the risk assessment, you need to total dose information. In order to get the total dose, you need to estimate the external dose and internal dose received by the animal that you studied. For the external dose, it could be derived from the little activity in the surrounding environment where they lived. For example, from the seawater, they might live in the seawater, they might be living in the sediment. So they're exposed to the radionuclides in that particular environment. We took that little activity concentration to estimate the external dose. In order to estimate the internal dose, we use the little activity in marine biota itself to derive into the internal dose. Once you got external and internal doses, you combine them together, you get the total dose as a result. Then we compare the total dose with the guideline value of 10 microgram per hour. If the total dose is below 10 microgram per hour, it means that there is no radiation impacts to be observed in the study animals. But if they receive radiation doses exceeding the guideline value, at this point we might have to introduce the remediation measures to reduce the radiation dose in their bodies to avoid the radiation impacts that could be happening in their body. Once we understand the basic concept of the radiation dose and risk assessment, in this study we use the ERICA assessment tool, which is widely available or freely available for you to download. This software, this predictive model is widely used in several countries in across the European countries. That's why we decided to use these ERICA tools for in our study. Here is results and some short discussion from our finding. On your left-hand side, you can see the radioactivity concentration of Cs-137 in the seawater from the Gulf of Thailand and from the Andaman Sea. We found a range of 0.43 to 2.41 millibecquerel per liter with an average of 1.29 millibecquerel per liter in the Gulf of Thailand, whereas a range of 0.40 to 1.35 millibecquerel per liter with an average of 0.8 millibecquerel per liter was found in the seawater from the Andaman Sea. When we compare the Cs-137 radioactivity in those from those two areas, we found a significant difference between those two areas. This is because of the seawater from the Gulf of Thailand might be receiving the large volume of water input from the several major rivers from the mainland. They might be having some kind of particles with the Cs-137 bringing them into the seawater, leading to the higher level of the Cs-137 in the seawater from the Gulf of Thailand. On your right-hand side, we got the information of the Cs-137 in the seawater before the Fukushima nuclear accident, and then we compare the especially from the Gulf of Thailand, and then we compare the these two results, and we found the significant difference between the pre and the post Fukushima Cesium-137
radioactive in seawater. This is because of the physical decay of Cesium-137. That's why we found lower Cesium-137 concentration in seawater, recently studied compared to the previously studied before the Fukushima nuclear accident. For the Cesium-137 in marine species, firstly we focus on the Gulf of Thailand. We found a range of 0.23 to 0.71 becquerel per kilogram in the N hexagon, whereas a range of less than 0.05 to 0.47 becquerel per kilogram with an average of 0.17 was found in S. elongata. A range of less than 0.05 to 0.27 becquerel per kilogram with an average of 0.12 was found in L. Duvasley. When we compare those values together, we found no significant difference between the pre and the post Fukushima values, except the radioactivity concentration in the L. Duvasley. For the radioactivity, Cesium-137 radioactivity in the marine species collected from the Andaman Sea, we found a range of less than 0.04 to 0.54 becquerel per kilogram with a mean of 0.18 in N hexagon, and a range of less than 0.01 to 1.08 becquerel per kilogram with an average of 0.17 in S. elongata, whereas a range of less than 0.03 to 0.33 becquerel per kilogram with a mean of 0.12 was found in L. Duvasley. But when we compare our results from two different locations, from the Gulf of Thailand and in Andaman Sea, we found no significant difference between the Cesium-137 radioactivity in the marine species collected from the Gulf of Thailand and the Andaman Sea for the post-Fukushima values. For the radiation dose calculation, you can see from this graph, you can see really clearly that the animal of interest receive low level of the Cesium-137 radiation doses compared to the guideline value of 10 microgram per hour. It means that there is no radiation impact or radiation effect could be observed in those studied marine species. And then when we compare between cesium doses in marine species before the Fukushima nuclear accident and after the Fukushima nuclear accident, you can see very clearly that the one that we recently studied have the lower level of Cesium-137 doses in their bodies. This is because of the decay of the Cesium-137 from the marine environment due to its physical half-life of 30 years. That's why the one that we study in this research has the lower level of Cesium-137 doses in their body. Again, similar to to those from the Gulf of Thailand, the marine species collected from the Andaman Sea showed the lower level of radiation doses compared to the guideline value of 10 microgram per hour. Again, it means that there's no, radiation impacts or effects that could be observed in those marine species. From these two graphs, it clearly showed you that the external dose is the main contributor to the total dose received by the study marine species in this study. Here is the conclusion of my talk. Lower Cesium-137 radioactivity was found in the seawater, and the economic marine species are recently studied. Higher Cesium-137 level in the seawater from the Gulf of Thailand was found due to large water input from several main rivers when compared to the Cesium-137 level in the seawater from the Andaman Sea. Cesium-137 doses received by the study local marine biota are well below the guideline value of 10 microgram per hour. Once again, there is no radiation impact or effects that could be observed in the study animals. Cesium-137 doses from the surrounding environment are the main contributor to the total doses. Finally, it could be concluded that the Thai marine ecosystem has not been radioactively contaminated by the Fukushima Daiichi nuclear power plant accident. Thank you for your attention.